Chapter 3 of the Stormwater Management Guidebook covers the Stormwater BMP specifications. In this video, we'll discuss permeable pavements. The guidebook is arranged such that the specifications for each BMP type are laid out in the same format, and it includes the following subsections. Permeable pavement is an excellent BMP that can be used in areas where you need to maintain the surface in a state where there's pedestrian access or vehicle access. The permeable pavement system in that case will function a dual purpose of allowing to have that use of the pedestrian or the vehicle access, as well as providing some stormwater management. The permeable pavement surface material can come in many different types. There are permeable pavers, pervious concrete are the two most common that we see. We also see quite a bit of porous rubber or play surfaces that are porous material. We see the plastic grid pavers less, but occasionally they can be used. In terms of stormwater management, the pavement surface material doesn't really matter as long as the system is designed per the manufacturer specifications and the surface material that's being specified is on the plans. So you have to design for the material, but there is a wide variety of materials that can be used. Here's a typical cross-section of a permeable pavement system. So you can see on that top is that permeable surface, so that grid paver or the porous asphalt or whatever it may be. Beneath that, there's typically a bedding layer to stabilize and level that surface layer. And then underneath that, there's the reservoir layer, which does the bulk of the stormwater retention. And beneath that, there's the uncompacted subgrade. Sometimes there can be a filter layer between those to make sure there's no migration of fines between the subgrade and the reservoir layer. In some systems, you have an underdrain. So this is a perforated pipe that will collect the runoff from the reservoir layer and conduct it to the storm sewer system. There are three different variations on the permeable pavement in terms of calculating the retention volume. So you can have the standard design, which is shown at the top left there, where you have the underdrain located right down near the bottom of the reservoir layer. There is an observation well in all of these cases going up to the surface of the permeable pavement so that you can look into that observation well, check to see that infiltration is occurring, there are no blockages in the underdrain, and also to perform maintenance. If there is a blockage, it can also serve as a clean out. On the other end of the spectrum at the bottom left, there's the enhanced without underdrain. So there's no underdrain in this system at all. There's infiltration capacity in the subgrade such that all of the runoff that goes in and percolates down and is stored in the reservoir layer of the permeable pavement can infiltrate into the subsurface. In the middle, there's this enhanced with underdrain system. So it's a kind of a hybrid of, on the top, a standard system, and then there's a reservoir, a sump underneath the underdrain. So you may have soils that have an okay infiltration capacity. They can infiltrate what's in that sump layer, but not the full reservoir layer if there were no underdrain. So it's a bit of a hybrid between the standard and the enhanced without underdrain. There are some feasibility criteria that are important to mention here. The ratio of external contributing impervious surface to permeable pavement area is maximum 5 to 1. All right, much lower 2 to 1 is recommended, but the absolute maximum is 5 to 1. So the key thing here, and as well for keeping the CDA to be as impervious as possible, is we want to limit loading of sediment that can clog the surface of the permeable pavement system. Right, so research has shown that highly pervious areas, so if there's a lot of sediment being contributed from the CDA, and if there's just too much contributing external area to the permeable pavement surface, it increases the rate of clogging because of that excess sediment loading. So we limit it to 5 to 1, but we recommend much lower. There are some other requirements, such as the water table depth, and setbacks from buildings and slopes that you can read about in the Stormwater Management Guidebook as well. Large storm events must be managed for the conveyance and criteria and pretreatment. So in the cases of permeable pavement, this can be done in a number of ways. So there can be an overdrain placed or an overflow inlet. You can put extra storage depth or underground detention. You basically have to ensure that in a large storm event, the excess runoff is going to go somewhere without causing a nuisance. Pretreatment is not required if the CDA is 100% impervious, but if you do have a source in the CDA that can contribute some sediment, a pretreatment filter strip is required. The permeable pavement design criteria include the following. So each layer has specifications on the material that can be used. So the reservoir layer, that main bulk of the retention occurs in that reservoir layer. And so there are larger stone in there with a larger pore space. So there's number 57 stone or number 2 stone typically in that area. Underdrains have to be PVC with 3/8 inch perforations, and they must be designed to drain within 48 hours, ideally slowly, right, with greater than 36 hours. So you're required in the underdrain to actually install a low flow orifice to slow down the flow out of that underdrain. If you have an infiltration sump, or if there's an enhanced without underdrain design, so that stored volume, whatever it may be in the infiltration sump or in the full depth of the permeable pavement, that must infiltrate within 48 hours. The filter layer between the subgrade and the reservoir layer is typically number 8 choker stone. And then, as I mentioned before, all permeable pavement systems have to have at least one observation well. The bottom slope must be as flat as possible because we're trying to encourage infiltration. We're trying to achieve retention in these systems. So if you cannot achieve a flat bottom surface slope or bottom slope for the permeable pavement because the surface slope is greater than 2%, then you can use this internal flow barrier or a kind of sort of subsurface check dam to create a level surface on the bottom, even though there is a sloped top surface. There are a number of key calculations. These are 2 of the equations in the Stormwater Management Guidebook for the permeable pavement design. Equation 3.3 calculates the time to drain for that storage layer. So for the enhanced design or the enhanced design with an underdrain, that sump layer, the depth of that reservoir layer multiplied by the effective porosity of the reservoir layer, which we use as 0.4 based on the size, typical size of the stone, so that's up here, divided by the field verified saturated hydraulic conductivity. So this is something that needs to be tested. You have to provide the test reports to show what the field verified saturated hydraulic conductivity, and there are requirements specified in an appendix of the guidebook showing how that test must be performed. So you can calculate the time that this storage layer will drain based on the depth of the layer, the porosity, and then the saturated hydraulic conductivity, basically how quickly that runoff is infiltrating out of there. And so that time to drain must be less than 2 days or 48 hours. The storage volume of the practice is calculated by equation 3.4. So the area of the practice multiplied by the storage depth in the permeable pavement layer, the depth of the practice times the porosity, plus this additional bit of storage that is given based on the kind of dynamic nature that as the reservoir layer is filling up, there's going to be some infiltration happening. So the time to fill the reservoir layer is assumed to be 2 hours. So this is a standard. So in those 2 hours, whatever infiltrates based on this hydraulic conductivity is also calculated and considered into how much storage you achieve, right? So the storage is the static storage on the left here and the dynamic storage on the right, multiplied by the area of the pavement, and you get the overall storage volume for the practice in cubic feet. So you can see for the standard design, you take that storage volume and you don't really take that into account for the retention value. The retention value for a standard design is just across the board 5 cubic feet per 100 square feet of practice area. Where the storage volume of a standard design can come into play for a stormwater management design is in the detention, which we'll talk about in a separate video, but that storage volume still can contribute to meeting your detention requirements. But in terms of retention value, in terms of meeting the swerve, it's a standard 5 cubic feet per 100 square feet of permeable pavement. It's also an accepted TSS removal practice, and what that means is that there's some sort of filtration mechanism occurring here. There's some settling and filtration that's happening to remove the solids that are in the runoff. And so in certain situations, you may need to achieve retention, but you also might need some additional treatment. So where this comes into play is often in the vehicle access areas. So vehicular access areas must achieve a certain level of treatment, which I won't go into detail on. But if you need this additional treatment, you can look to these practices such as permeable pavement that are accepted TSS removal practices. For the enhanced design without underdrain, so the other end of the spectrum, where there's no underdrain at all, the retention value is equal to the storage volume, excuse me. So that full storage volume, all of that goes towards the retention value. That hybrid system, where the enhanced design with underdrain, that storage volume in the sump, that infiltration sump at the bottom, all of that storage volume goes towards retention value. But for the part on the top, which is basically like a standard permeable pavement, you get an additional 5 cubic feet per 100 square feet of practice. So what's in that sump, what goes down and gets fully infiltrated, that storage volume calculation is equal to the retention value plus another 5 cubic feet per 100 square feet of the practice for the top part of it.